This dryer motor is drawing about 4 amps of current, which is typical for this type of motor. What would you say, however, if I told you that I could reduce the current draw of this motor to about 1.5 amps with no loss in performance? In this video, we'll do just that by utilizing something called power factor correction. I'll first, though, explain what power factor is, why it drastically and unnecessarily increases the current draw of such a motor, and how it can be corrected with an appropriately sized capacitor. At the end of the video, I'll explain how power factor affects you, the average consumer, as well as factories and even utility companies. First, this video is for educational purposes only. The demonstration involves dangerous voltages that can cause serious injury or death. I am using an isolation transformer and taking proper safety precautions. Do not attempt to do this yourself. You might think it isn't possible to reduce the current draw of this motor to around 30% and not affect its performance. In reality, though, the motor is only utilizing 1.5 amps of that current. The rest is wasted energy because of the motor's inductance and resulting low power factor. Power factor is a measure of how much real power is being used by the motor compared to the apparent power being delivered to it. Apparent power is simply volts times amps. In this case, 120 volts times 4 amps is equal to about 480 VA. Because this motor largely is an inductive load, a significant portion of the current, about 2.5 amps, is out of phase and does no useful work. This out-of-phase current is reflected back to the utility company and causes unnecessary resistive heating in both your house wiring and the utility company's power lines. Split-phase induction motors like this one are notoriously inefficient, with very low power factors. As shown by this watt meter, the power factor is about 0.33, meaning only about 33% of the supplied power is actually being converted into mechanical or useful work. You can clearly see how out of phase the current and voltage are on the oscilloscope, and that's why the power factor is so low. Our goal is to bring the voltage and current back in phase, meaning that they rise and fall together. This synchronization is essential for efficient power transfer. A perfect power factor is 1.0, where voltage and current are perfectly in phase, which is what we'll try to achieve in this video using power factor correction. We'll do that by calculating the value of a capacitor to place in parallel with the motor. This capacitor cancels out most of the unused reactive current. To determine the correct capacitor value, I'll use a power factor correction calculator that I developed, which uses trigonometry and algebra under the hood. You can find this calculator at techcircuit.org, linked below in the description. If you want a deeper dive into power factor correction and the math behind the calculator, check out video 109 on this channel, also linked in the description. In the calculator, I'll enter the supply voltage of 120 volts, the frequency of 60 Hz, the current draw of 4.1 amps, the reported power factor of 0.33, and the desired power factor of 1.0, which is a perfect power factor. And here's our result. The calculator tells us that a capacitor value of around 85 microfarads should bring us to unity or perfect power factor of 1.0. It also tells us what the expected current draw will be once power factor is corrected, which you can see is less than 1.5 amps. I've got a few motor run capacitors on hand, so I'll combine them in parallel to get as close as possible to that value, which turns out to be about 93 microfarad, within 10% of our calculated value. This won't get us to a perfect power factor, but it'll get us really close, and we'll get our final current draw to less than 1.5 amps. Now I'll wire this capacitor bank in parallel with the motor. Again, this is for demonstration purposes only. Do not try this at home. Okay, it's all wired up. I'll go ahead and flip the switch and let's see what we get. Now we have a current draw of 1.4 amps, which is really close to what we predicted. The power factor is nearly 1.0. On the scope, the voltage and current waveforms are almost perfectly in phase, exactly what you want for efficient operation. You might be wondering, well, if the motor is only drawing 1.4 amps, how do I know it's still performing the same? Well, if I use this clamp meter right here at the motor terminals, you'll still see that it's drawing over 4 amps just like before. Here's what's happening. The out-of-phase current is now circulating between the motor and the capacitor, not between the motor and the utility company. The motor still behaves the same. It still gets the original current, but the power source now only has to supply 1.5 amps of in-phase real current. This reduces resistive losses in your home's wiring and along the utility's power lines. By simply placing a properly sized capacitor across the motor, we've improved its power utilization from around 30-something% to around 95%. That's a huge gain in efficiency. This is one of the main reasons of run capacitors and split capacitor motors, as they improve the power factor and promote smoother, more efficient operation. In fact, power factor is a critical factor in how efficiently a load uses electrical power. A low power factor means more current is drawn than is actually needed, leading to wasted energy and increased heat in wiring and transformers. This is one of the key reasons why in many modern appliances and HVAC systems, they are switching to BLDC or brushless DC motors. Unlike traditional split-phase motors, BLDC motors use electronic commutation and typically have near unity or near perfect power factor, meaning they draw only the power they actually use. This makes them vastly more efficient, especially over long-term operation. So how does this affect you, the average consumer? Fortunately, most utility companies don't charge residential customers for apparent power, or VA, which is voltage times current, only for real power in watts. That's good news for homeowners. However, low power factor still negatively impacts the utility grid by increasing transmission losses and infrastructure wear. These added costs eventually affect everyone through higher electricity rates. For commercial and industrial customers, the stakes are higher. They're often penalized for low power factor, which is why businesses are incentivized to correct it using capacitor banks, active filters, or investing in equipment like BLDC motors that naturally maintain a higher power factor. I hope this video has been helpful and informative. If so, please give it a like and subscribe to this channel for more practical, hands-on videos about electrical theory. Thanks for watching.